Okay. Good afternoon, everyone. I'm Quentin Jullien from CSTB, le Centre Scientifique et Technique de Bâtiment, which can be traduced by Technical and Scientific Center for Buildings. And more precisely, I work in the Safety, Structure and Fire Department, an accredited laboratory in France. And I will present you some work done this year on stochastic analysis of egress simulation. First, I will present you the context and the aim of the study, and then the method principle for statistical aspects, then the hypothesis of the model, and some reference study cases, and the analysis and the conclusion. And I precise now that this method and the study conducted this year are a preliminary work and need some improvements. I will back on this point later. Well, let me start with the French regulatory context before the context of this study. In France, there is no possibility to use egress simulation to prove that a building is safe. The regulations are only prescriptive in this field. And so we started a reflection from some years ago on some methodological proposition to use properly egress simulation to convince ministries, and we still move in this direction. I know that there are regulations around the world that allow performance-based approach, and so I hope there is no two commonplaces in this presentation. Hence, the starting point is that the use of egress simulation model in performance-based analysis relies on the confidence in the input data and the output data. But data strongly depend on a large number of parameters, because these data are linked to the human behavior, and so the results are prone to be scattered. And this study proposed an analysis method to deal with it. Thus, the aim of this study is to create a method to analyze the stochastic aspects of an egress simulation model. And the cut point that is the method is based on statistical estimation of the distribution quantiles of the output parameters. And the result considered in most of studies is the RSET, and it will be the case in this study. The RSET is a required safe egress time. In other words, the time takes by an occupant to evacuate a building safely. And the benefit of this method is to provide quantitative information on the RSET and to justify the number of simulations to obtain a relevant output precision level. In addition to what has been said previously, the egress phenomena is scattered in itself, because evacuating a building can occur in a lot of different ways. And this method tries to deal with the whole range of possibilities. A stochastic approach is used for that, generating distribution function for each output. And the random aspects are processed by the mean of the confidence interval concept. Let's take an example unrelated to the egress simulation for the moment, with a sample of n realization of a random variable that follow a normal law distribution, with a confidence interval IP for each quantile alpha, and a level of confidence P here 90%. This is the formula of the confidence interval, with F tilde, the empirical distribution function, and C, the quantile linked to the normal law distribution. C is equal to 1.645 for P equal to 90%. And I precise, whatever the law taken by the sample, the confidence interval is calculated as it. And the distribution function is said empirical as opposed to the real distribution function, which is generally unknown. And the empirical distribution function is composed of the random realization rank in ascending order to constitute the empirical distribution function. And by construction, the empirical distribution function, the black curve, is included in the confidence interval with the lower bound and the upper bound. Whereas the real distribution function is included in this interval, but with a probability here of 90%. And the level of confidence is chosen arbitrarily. Its value must be discussed and depend on the desired level precision. And the following observation come from the previous figure. A random variable can have no theoretical maximum. And even if there is a maximum value, the finite size of the sample prevents from calculating this maximum value. We can see on the right corner. We cannot reach the theoretical maximum value. And so only percentiles are available. And these available percentiles increase with the growth of the sample size, and the confidence interval width decrease with the growth of the sample size, which is an interesting property. So the required number of simulation is set by the desired precision and the order of the desired quantile. These observations are applicable to egress simulation. However, before to apply this method to an egress simulation, the hypothesis must be presented. The numerical tool used in this study is BuildingExodus, but statistical processing can be performed with any simulator. And I just remind that BuildingExodus is based on a discretization of space in a node of 50 centimeter by 50 centimeter. And the connection model used is the one of Moore. That is to say that an occupant can move to any adjacent nodes, even those in diagonal. And this figure presents the test case geometry, simple test case geometry with a single room of 256 square meters, that is to say 16 meter wide square, with 4 exits of 3 meter wide, one by side. And this test case is simple enough to set up the analysis method without modeling difficulties. The result values are meaningless. This is the trend which is important, and not the value. The geometry will be more complex and realistic in further study. Next, the behavioral hypothesis. Concerning the occupants are the same leaderships. It implies a conflict resolution time include between 0.8 seconds and 1.5 seconds, and the fixed value of 1.15 seconds will be used to. It is the average value of the previous interval. The occupants have the same patience. It corresponds to the delay before an occupant starts to redirect himself if there is a queue. 10 seconds is steady. The occupants are valid and have a speed of 1.2 meters by second, and a response time, RT, of 15 seconds or variable between 0 and 30 seconds. In the study, the response time is the delay before the occupants begin to move toward the exit. And finally, they act independently of each other. That is to say, if an occupant begins to move toward the exit, he will not make another occupant move before its response time is elapsed. And in addition, I precise that fire conditions are not used in this study. And some modeling parameters are fixed, and some others are variable and randomly drawn with an uniform law. It is not linked to the proposed analysis method. It is by simplification for this study. Now that the bases are presented, let's begin with the reference study case. For this case, the occupants are randomly located in the room and drawn between 1 and 1,000. This figure shows the empirical distribution function and the confidence interval bounds for 1,000 simulations and 100 simulations. And the level of confidence is of 90% for all cases. And for this presentation, I'm not focused on the numerical results, but on the analysis of the results and on the conclusion about them. The numerical results are more detailed in the paper. This simple case demonstrates that it's impossible to statistically determine a RSET maximum. Indeed, extreme percentile have a confidence interval with infinite bands. In any case, a RSET max is bound to a catastrophic scenario, though it seems preferable to retain a higher percentile. Consequently, in this study, we use the 95th percentile. And obviously, this value is a K parameter and must be discussed because it is difficult to say a priori what is acceptable as value. And for example, if the empirical distribution function is near of a vertical line, the difference between the 90th percentile and the 95th is meaningless. Then, the results are consistent with the observation made previously. The width of the confidence interval decreases with the increase of the number of simulations. And furthermore, it is not exposed in this presentation, contrary in the paper, but beyond 1,000 simulations, the gain and the confidence interval width against the time spent to perform the simulation decrease drastically. And moreover, there are at least 3 separate evacuation patterns according to the number of occupants. It is an interest of the method to identify this pattern. We can see the first pattern at low density between 22 and 37 seconds The second pattern had medium density between 37 seconds and 72 seconds, and the last one had high density between 72 seconds and 83 seconds. We can identify a pattern by change of flow. And this pattern are also identifiable when you represented the occupant number against the RSET obtained. The scattering varied from a pattern to another one. And these patterns are used to get rid of the occupant density influence. And the density for each pattern is fixed against the average number of occupants in this pattern. 197 for the first pattern, 610% for the second one, and 927 for the last one. The influence of each pattern of different parameters is tested for each pattern. And moreover, 1000 simulation with an occupant number randomly drawn between 1 and 1000 present few simulations with the same number of occupants. It makes it difficult to quantify the influence of the position, for example. And perform 1 billion of simulation to have enough simulation with the same number of occupants is meaningless from an engineering point of view. In any case, the method provides additional elements to understand evacuation behavior, even in the simplistic case. After this reference test cases, different parameter sets are tested to measure the influence, and the tested parameters are the conflict resolution time, the position of the occupant, and the response time. And there are 1000 simulations for each pattern. And the first test case is the closest to a default set parameter of BuildingExodus. The second one is to test the variability of the output results with all the input parameters fixed. And the third one at the randomization of the position of the occupant against the first one. And the fourth one tests the variability of output results when all the input parameters are variable. Then, this figure shows the empirical distribution function, and it is obvious that the empirical distribution function is not uniform. It is linked to the variability of the conflict resolution time and to the history effect. I call history effect the consequences of a conflict which leads another conflict and so forth. Then, before to go further, here are notation to make quantitative comparison. IP 95%, the confidence interval of the 95th percentile, LIP 95%, the width of the last one, to quantify the spread of the result around this value. IP 5%, 95%, the interval between the lower bound of the 5th percentile and the upper bound of the 95th percentile. LIP 5%, 95%, the width of the last one, to quantify the spread of the results. And the last one to normalize the spread by dividing by the 50th percentile. Thus, this figure compares the result of the test case number 2 and number 1. And for reminder, the difference between the test case number 2 and number 1 is on the conflict resolution time. It is fixed for the second one and variable for the first one. And by convention, the case with the smallest number is the left part of a couple. And there is one couple for each pattern, 1, 2, 3. And for two results, LIP 95% and LIP 95%. And the observation are the following. Firstly, most of the variability comes from the history effect, because the difference between each part of each couple is very weak. And secondly, confidence interval with variation are not intuitive, because at first sight it appears logical that the test case number 2 has the confidence interval width smaller because the parameters are all fixed. But it is not the case for the pattern number 1 for LIP 95% and for pattern number 3 on LIP 95%. Then, this figure compares the result of the test case number 3 and number 1. For reminders, the difference between the test case number 3 and number 1 is on the position of the occupant. It is variable for the test case number 3 and fixed for the test case number 1. And the observation is the following. The position has more relative influence on low and average density, which is logical, because with a quadratic room, the occupant position is meaningless. So the method gives a consistent result on this point. Then, this time, the comparison is between the test case number 4 and number 3. For reminder, the difference between those two is on the response time. It is fixed for the test case number 3 and variable for the test case number 4. And the observations are consistent with what it could be expected. The variability of output parameter increase with the one of the input parameters. Again, the method gives consistent result. So, the synthesis result from a qualitative point of view are by decreasing order the occupant number, which has the very important influence on the RSET, and then the occupant position and the response time, which have an important influence on the RSET, and finally, the conflict resolution time. So firstly, from a statistical point of view, it is possible to observe these influences, and secondly, by this study, it is possible to see that this difficult value to quantify has a negligible influence, and so there is no interest to work on this value. Thus, the method assets are to give a methodological justification to the RSET quantification, to assess the number of simulations to perform to get an appropriate confidence interval with, and to estimate quantitatively their influence on the RSET of the input parameter dispersion. And at this point of the presentation, I remember that the results obtained in the study are preliminary results. But they permit to better understand some phenomena occurring during the evacuation, to show nonlinear effect of input parameter on the RSET on some non-intuitive complex behavior, and to raise the question of what RSET is, on what is an adequate failure probability, because it's a fundamental question. And finally, to conclude, during this study, it has been possible to interpret the influence of variability of an input parameter to an output parameter, to quantify the number of simulations required to have the short confidence interval, and obviously there is still a lot of work, because to make an engineering level tool, because currently the method developed here has been carried out by simple automation script and to find relevant input data. Nevertheless, the method can help to sort out the main influence and prioritizing which evacuation test to perform in order to get this information. And finally, to conclude, the next novel is to test more realistic cases, to test cross-interaction falsely by experimental plan, for example, to compare to some evacuation trials, and to industrialize the method and tools dedicated to stochastic analysis, and to compare different simulation tools. And again, discuss what is an acceptable failure probability. Thank you for your attention.
Do we have questions? No questions. Okay, well, thank you very much. I appreciate it.